Kinetics studies the reaction rates. The activation energy is this energy here that represents the barrier that it takes for the starting material to reach up to the transition state. Some of the factors that affect the reaction rates are concentration, because the higher the concentration, the higher the reaction rate, and the higher the temperature, the higher the reaction rate as well. So the higher the temperature, the higher the reaction rate. So things that do not matter at this point are the delta G, the delta H, and the Ka, because those are thermodynamic terms. The energies that represent the delta G, the delta H, or the K equilibrium do not have anything to do with the rate of the reaction. So the energy tell us, so the thermodynamics tell us if the reaction is going to proceed or not, but the reaction rates tell us how fast is that reaction going to proceed. So the rate law is represented by this expression right here. So the rate is equal to the concentration of the reactants times the K. The K is constant. So fast reactions will have large rate constants, and slow reactions will have small rate constants. So the rate constant and the activation energy are inversely proportional. So when you have a high rate constant, it means that the reaction is going to be fast and that it's going to have a small activation energy. And so the rate of a reaction, it's K, that constant, multiplied by the reagent's concentration. When the reaction happens in just one step, just as this one right here, all the reagents matter. So both the starting materials, in this case, we have this AB molecule and the C minus molecule, they both matter. So that's why the rate of this reaction will be 2, because we have a 1 right here and a 1 right here. And so we add them, and that's how we get these 2. The rate of the reaction is determined by the reagent's concentration. And because here we have A, B, and C, and both of them matter when the reaction is just one step, so the reaction will happen in one step, then we'll have a rate of the reaction 2. I know it's kind of counterintuitive, so we have a reaction that happens in one step, but the rate of the reaction is 2. But it is because all the reagents involved matter. On the opposite, when we have a two-step reaction, remember we talked about one of the steps being rate determining. So even though this is a reagent and this is also a reagent, right, that second part does not matter so much, because the rate determining step is just the first one, and so that's why the rate will be determined only by the concentration of this reagent right here. So the rate for a two-step reaction will be 1, because only that reagent will matter. So for a two-step reaction, the rate determining step makes that this is a first order reaction. I'm going to explain it one more time. When we have a one-step reaction, all the reagents involved in it matter, and that's why we have a second order reaction. But when you have a two-step reaction, only the rate determining step matters, which in this case is this one right here. And that rate determining step only has one reagent, and so that's why I only put the concentration of that first reagent of the rate determining step right here, and that's why I end up with a 1. So even though the reaction is a two-step reaction, this will be a first order reaction. It's very counterintuitive, but it is how it was defined. And so I'm sure you've heard about catalysts. So what catalysts do is they change the activation energy of the reactions, lowering that activation energy and making the reactions proceed with a smaller activation energy, and they will proceed in a faster way. So here, for example, when we mix acetic acid and ethanol, this reaction will eventually happen. But by adding sulfuric acid, this reaction happens in a much faster way and in a much efficient way. And so this is exactly what happens. So we have a reaction in red that will eventually happen, but we need to put more energy to reach this transition state. However, when we add the catalyst, which is the blue line, what happens is that it lowers the activation energy, making the reaction go faster. And enzymes, what an enzyme is a biochemical catalyst that is present in our bodies and in many other places in nature. So for example, if we see this lactose, we have this lactose molecule, what happens is that our body can break it down, but it will take forever for it to break it down. And so what this enzyme right here does, the green molecule, what it does is that it's a catalyst, but it's an enzyme, so that's why it's a biological catalyst. And so what it does, it breaks here, you see, it breaks that lactose molecule into one molecule of galactose and one molecule of glucose. And so again, these enzymes are just biological catalysts that accelerate the rate of the reactions in our body.